Thank you very much. I would like to thank the organizers for the opportunity to speak here and for this wonderful conference. As the title states, I'm going to talk about acyclic complexes and finitistic dimensions. And my talk has three parts. First, I want to recall what are finitistic dimensions and some basic properties of them. Afterwards, I'm going to talk about acyclic complexes, and specifically, we are going to be interested in the question of whether they are contractible. So acyclic complexes, I just mean an exact sequence, and contractible is another name for null homotopic. So I want to know if such a complex is always contractible or not. So these two things seems completely unrelated, but on the last part of the talk, I'm going to talk about a very strong connection between these two kind of questions. So let me start talking about finitistic dimensions, or maybe some background to this problem. So I want to study rings, and specifically I'm interested in understanding their homological algebra. And I want to understand how complicated it is. And usually the way to measure how complicated is homological algebra of a ring is by introducing global dimension. So I just look on all A modules and compute the projective dimension and ask what's the supremum of this. And this is probably the best homological invariant we have to measure how complicated a given ring is. But the problem with this is that often this is infinite, even in nice cases. I mean, we know from work of Searle that, for example, for commutative Noetherian rings, let's say of finite cool dimension, having finite global dimensions means you are regular, and there are many singular varieties in our world. So this global dimension kind of misses this the entire singular world in terms of measuring how complicated a given ring is. So let me give probably the most classical example about this phenomena, and this is the ring of dual numbers. So I take a field K, and over the ring of polynomials, I look on this quotient, kx modulo x squared. This ring is very simple. In fact, modules over this ring are direct sums of either A or the field K. But the field K has infinite projective dimension. So the global dimension of this very simple ring is infinite. But if I only look on modules of finite projective dimension, things become much easier, because if I just take the supremum of projective dimension among modules which I already know have finite projective dimension, well, as I said, in this case, the category of modules over this ring is so simple that any module of finite projective dimension in this case is actually projective. So this number, while the global dimension is infinite, this number, this alternative global dimension, if you wish, is actually zero. So in this simple case, this measurement reflects better how simple this ring is. And so this kind of idea has led Kaplansky already in the 1950s to give the following definition. So the definition is that the finitistic projective dimension of a ring is the supremum of projective dimension, but taken not among all A modules, but only among all A modules of finite projective dimension. So I restrict to modules of finite projective dimension, and among them, I take the supremum of projective dimension. And this is sometimes called the big finitistic projective dimension, because we can also play the same game while we restrict attention only to finitely generated modules. And if we do that, we get something which is called the small finitistic projective dimension. So the definition is the same, except that now we look only on finitely generated modules of finite projective dimension and take the supremum of projective dimension among these modules. Okay. So let me tell you what is known about this first in the case of commutative rings. So for commutative rings, we know essentially almost everything. the situation is that for commutative rings we know all we want to know, and for non-commutative rings we know essentially nothing. So let me explain this. So first, already in 1960, Bass showed that if I have a commutative Noetherian ring and they take a number which is at most its cool dimension, I can always find a module with this given projective dimension. So in particular, the finitistic dimension of a commutative Noetherian ring is always at least the cool dimension. And for a while, this what was known for about, I think, 15 years, and it was conjectured that the converse holds as well, and indeed, in a beautiful and very deep paper from, I think, 1971, published in Invenciones, Renaud and Grousson showed that the converse holds, namely, if you have a commutative Noetherian ring of a given cool dimension, any module of finite projective dimension has projective dimension at most the cool dimension. So if we combine these two results, we see that the finitistic projective dimension of a commutative Noetherian ring is simply its cool dimension. What about the small finitistic dimension? Well, this is even easier, at least in the local case, because the Uslander-Buchsbaum formula just tells you that any Noetherian local ring has small finitistic dimension equal to the depth of the ring. So just the maximal length of an irregular sequence. And then it's nice to combine these two and ask, for a Noetherian local ring, when is the small finitistic dimension equal to the big finitistic dimension? And we see here that, well, the big one is cool dimension, the small one is depth. So small equals big finitistic dimension for Noetherian local rings, precisely for Cohen-Macaulay rings. So this is a way to characterize Cohen-Macauliness, a completely homological way, for which you only need to know what are the modules of finite projective dimension, and the modules of finite projective dimension actually know if your ring is Cohen-Macaulay or not. So this is, I think, something nice. This is all I have to tell you about commutative rings, because this is pretty much everything we can ask in this case. But let's switch now to non-commutative rings. And then the situation is much, much more complicated. And even if I restrict to finite dimensional algebras over a field, which are kind of the smallest non-commutative rings, here are three questions I can ask them. So the first question is, are they Cohen-Macaulay in the sense above? So is the small and the big finitistic dimension equal? My second question is, the small finitistic dimension is finite? And the third one, is the big finitistic dimension finite? So these questions were already asked around 1960. And quite amazingly, even today, we only know the answer to the first question. So I think in 1991, Husgen Zimmerman showed that, in fact, the first question has a negative answer. So there exist finite dimensional algebras for which the small finitistic dimension is strictly smaller than the big finitistic dimension. I think her example was where the difference between them was only one, but we now know that the difference can be as large as you want, but finite. So the question whether these finitistic dimensions are finite for finite dimensional algebra, they remain completely open, and we don't know any example of a finite dimensional algebra for which the finitistic, either of the finitistic dimension is finite. There are, of course, some classes for which we know that it is finite, but no example is known where it is infinite, and we don't have a proof that it is always finite. And these two questions are known as the small and the big finitistic dimension conjectures. Of course, the big one implies the small one, because if all modules of finite projective dimension have a bound on their projective dimension, then the same is true for finitely generated modules. And you can also ask them for Artin algebras and also for certain other classes of rings, and they are open, of course, in these more general cases as well. And these conjectures are very important, not only because they are open for more than 60 years, but also because they imply many other conjectures. For example, there is a
classical questions about Gorenstein symmetry, which asks if you have a nice Noetherian ring which has finite injective dimension on one side, you want to know whether it has finite injective dimension on the other side as well. This is an open problem. And the finitistic dimension conjecture implies it. And there are some other very important conjectures of this type which also follows from the finitistic dimension conjecture, like the Uslander-Reiten conjecture, the generalized Nakayama conjecture, and many others. So this is a difficult and important open problem. Okay, and now for the second part of my talk, I want to talk about something which seems completely different. And this is acyclic complexes. And most of the time, my complexes will be complexes of projective modules. So I have a ring A, and I will always look on co-chain complexes. And they are called acyclic if all their cohomologies are zero, meaning they are exact sequences. Now, an acyclic complex is contractible if the identity map is null homotopic. In this case, if I already know it's acyclic, it's easier to explain what it means. I can take the cocycle, the n cocycle module denoted by Zn of M, and then because this complex M is exact, this gives rise to a short exact sequence for each n, Zn of M going to the n part of the complex, going to Zn plus 1M, going to 0, and saying that the complex is contractible is just equivalent to the sequence being split exact. Now, if I assume, which I will, that my complex is a complex of projective modules, then saying that this is split exact just means that each of these cocycle modules is itself a projective module. So for an exact complex of projective modules, being contractible just means having projective cocycles. So here are some examples. So the first example, which trivially holds over any ring, is that if you have a bounded above co-chain complex of projectives which is exact, it is always contractible, and this is one of the most basic facts in homological algebra. I mean, one way to see this is that such a complex is a projective resolution of the zero module, but any two projective resolutions of a module are homotopy equivalent, and the zero complex is also a projective resolution of the zero module. So this complex is homotopy equivalent to the zero complex, hence it must be contractible. But not all exact complexes of projectives are contractible. So returning to the ring of dual numbers we had earlier, I can take over it the following co-chain complex, which has A, the ring itself, in all of its components, and all the differential maps are multiplication by X. This is again an acyclic complex of projective modules, but it's not contractible. Well, if it were, then if I apply any additive functor to it, it will remain exact. But if I tensor it with the field itself, I get something which is not exact. I get this complex which has cohomology in every degree. So this shows to you that this complex is not contractible, but it is an exact complex of projectives. By the way, it's also an exact complex of injectives. So this ring is, of course, self-injective. Anyhow, here's a more complicated example, much more complicated, and it's recent from 2023. It's due to Kanonako. And this example is the following. Let me take the ring of the quotient ring of a polynomial ring, of a non-commutative polynomial ring in infinitely many variables, and then I quotient out by the polynomials x1 times x2, x2 times x3, x3 times x4, etc. So this is a very, very complicated, very non-Noetherian ring, very non-commutative also. Over this ring, I can take the following acyclic complex of projectives. 0 goes to A, etc. And the differential maps are multiplication by x1, multiplication by x2, multiplication by x3, etc. Because of these relations that I imposed, this is an acyclic complex of projectives. Again, this is not contractible because I can again quotient out by all variables and get a complex all whose components are the field and the differential being 0.
So this is a bounded below a cyclic complex of projectives, which is not contractible. So then, if I were you, I would ask, why am I giving you such a complicated example? And also, how is this related to finitistic dimensions? So what I want to show to you is that, in fact, this question of the existence of such complexes is actually very much related to finitistic dimensions. And also, the reason I give you such a complicated example is that no simple examples can exist of a bounded below a cyclic complex of projectives, which is not contractible. So here's a recent result that Nakamura and Thompson were gracious enough to write as an appendix to a recent paper of mine. And it says that if you have any ring whose finitistic dimension is finite, then any acyclic bounded below complex of projectives is contractible. And let me give a very short proof of this, because it's quite easy. You see, for any n, because my complex is acyclic and bounded below, if I trim it at step n plus d plus 1, I get this exact sequence, which is just a projective resolution of the n plus d plus 1 cocycle module of this complex. Well, because this complex is bounded below, this projective resolution terminates at some point. So this just means that this cocycle has finite projective dimension. But if we assume that the finitistic dimension is finite, then its projective dimension being finite is at most this d. And if you have a module of finite projective dimension, d, at most d, then any d-syzygy of it will be a projective module, but the d-syzygy of this is just the n cocycle of this complex. So what this means is that any n cocycle of my acyclic complex of projectives is projective, and as we have seen, this implies it is contractible. Okay, so this works for any ring of finite finitistic dimension. In particular, this then is true for commutative Noetherian local rings, because a Noetherian local ring has finite Gruhl dimension, hence finite finitistic dimension. It's not hard then to show that this property remains true under localization, so you can actually deduce that over any commutative Noetherian ring, any bounded below a cyclic cochain complex of projectives is contractible. So this helps to explain why I had to give such a complicated example, or why it had to be non-commutative. In fact, there are no commutative examples, and I learned recently that you can even remove the word Noetherian here. So actually, over any commutative ring, any bounded below a cyclic cochain complex of projectives is contractible. Okay, now let me go back to this result of Nakamura and Thompson. It says that if the finitistic dimension is finite, then any acyclic bounded below complex of projectives is contractible. Is there any chance that the converse of this will hold? Well, in general, this cannot be. Because you see, there are commutative Noetherian rings of infinite Gruhl dimension. Nagata showed us that there exist such rings. And then by the result of Bass we had before, they have infinite finitistic dimension, but I just mentioned that over any commutative Noetherian ring, any acyclic bounded below complex of projectives is contractible. Okay, so in general, this result of Nakamura and Thompson does not have a converse, but actually, for most rings, it does have a converse. And for this, we need the notion of a dualizing complex. So I don't have much time, so I will just present you the definition of what's a dualizing complex. So it's something that lets you generalize the duality that you have, that a finite dimensional vector space is isomorphic to its double dual. It's something that you can do over many, many rings. And I will just say that this is a notion first defined by Grothendieck and in algebraic geometry, and then by Eccoutieli in noncommutative algebra, and later many people, including Eccoutieli, Zhang, Vandenberg, Jorgensen, Krause, Inger, and many others studied this. What's important for us is that finite dimensional algebras have dualizing complexes, and Artin algebras have dualizing complexes, and actually most Noetherian rings that arise in nature have dualizing complexes. So they are everywhere. Most rings that you work with probably have a dualizing complex. And so my first main result that I want to state says that if you have a two-sided Noetherian ring with a dualizing complex, then in fact the question whether the finitistic dimension is finite is equivalent to the question whether any acyclic bounded below complex of projectives is contractible. And you can also do the same with injective modules. So for such a ring, the finitistic dimension is finite if and only if any acyclic bounded below complex of injective right A modules is contractible. So everywhere I worked with left modules, but if you want to work with injectives, you need to look on injectives on the right side, not on the left side. So it turns out that these very basic homological properties, which are kind of dual to what we are used to, so we are used to the fact that bounded above a cyclic complex of projective is contractible, but if you want the converse, for most rings, it's equivalent to having finite finitistic dimension. Now, I also want to say something about the small finitistic dimension. Everything I said so far was about the big finitistic dimension. So clearly, if the big one is finite, then the small finitistic dimension is finite. But using the above, I can actually tell you when the converse holds. So using this and some results of Neyman, I can show that if a Noetherian ring with a dualizing complex has small finitistic dimension being finite, then its big finitistic dimension is finite is equivalent to the fact that any acyclic bounded below complex of projective is a direct limit of a cyclic bounded below complex of finitely generated projectives. So if you wish, this question becomes a kind of Lazard theorem, but you have to work only with acyclic complexes of projectives which are bounded below. You want to know if you can express them as direct limit of such complexes, whose components are also finitely generated projectives. And the last thing I want to mention is that this is also very much related to a recent result of Ricard. So let's recall that the localizing subcategory generated by injective modules is the smallest triangulated subcategory of the derived category, of the unbounded derived category, which contains all injective modules and is contained under infinite direct sums. And what I can show is that for such a nice Noetherian ring, which has a dualizing complex, if the injective modules generate the derived category in the sense of localizing subcategories, then any acyclic bounded below complex of projectives is contractible. So if we combine these two main results, I get that for a two-sided Noetherian ring with a dualizing complex, if the localizing subcategory of the injectives is everything, then its finitistic dimension is finite. And let me just mention that this was first proved by Ricard for finite dimensional algebras over a field. This was actually a question that Bernard Keller asked in 2001, and Ricard showed that it's true for finite dimensional algebras about 5 years ago. And so my new result says that actually it's true in this much wider context of Noetherian rings with a dualizing complex. And let me also mention that this is the best you can do, because if you don't have a dualizing complex, this is wrong. Even if there are rings, Noetherian rings, without a dualizing complex for which the injectives generate, but the finitistic dimension is infinite. I'm essentially done, but maybe if I have 1 or 2 more minutes, let me just mention that. So this results kind of gives you a hint that you should study finitistic dimension using derived categories. But I would claim that while the derived category certainly knows if the finitistic dimension is finite, it's not the correct place to study this question. So if I go back for a minute to this main result tells you that to understand finite finitistic dimension, you want to understand acyclic bounded below complexes of projectives or of injectives. and you want to know if they are contractible. So you want to understand if in the homotopic category of projective models or in the homotopic category of injective models, whether something which is acyclic is zero. And the category, the homotopic category of injectives which are acyclic is known as the stable category or the singularity category of the ring. So essentially what these results tell you is that the correct place to study the finitistic dimension conjecture is the singularity category of the ring. And this category, the singularity category, knows whether the finitistic dimension is finite or not. So I stop here. Thank you.